faster than light? Einstein versus Bohr, the Great Duel, 2025 new proof. In 1927, the two greatest minds in physics stood face to face in Brussels. Albert Einstein declared, "God does not play dice with the universe." Niels Bohr replied, "Einstein, stop telling God what to do." Their argument would determine the nature of reality itself, and nearly a century later, it's still not settled. Welcome to Sleep Entangled, where the greatest scientific controversies and contemplative wonder merge into late-night journeys. If you find fascination in the clash of brilliant minds debating the deepest mysteries of existence, remember to subscribe and let curiosity guide your nights. Now settle in, breathe deeply, and let's witness the most important argument in the history of physics. Chapter 1. The most important room in history. Brussels, October 1927. Picture a room in Brussels, Belgium. October 1927. The Hotel Metropole, elegant and grand, its chandeliers casting warm light on polished wood and velvet chairs. 29 physicists have gathered for the 5th Solvay conference. Their topic, electrons and photons. But this is no ordinary scientific meeting. Look at the assembled minds. 17 of these 29 people have won or will win Nobel Prizes. Max Planck sits near the front, the man who discovered the quantum of action in 1900, launching the revolution none of them fully understands. Marie Curie, the only woman in the room, twice a Nobel laureate, observing with keen intelligence. Erwin Schrödinger is here, fresh from deriving his wave equation. Werner Heisenberg, young and brilliant, architect of the uncertainty principle. Wolfgang Pauli, famous for his sharp wit and sharper physics. Paul Dirac, quiet and mathematical, already glimpsing the antiparticle that will bear his prediction. Louis de Broglie, who proposed that matter has wave properties. Max Born, who interpreted the wave function as probability. And presiding over the conference, Hendrik Lorentz, the Dutch physicist whose transformations would become foundational to Einstein's relativity. But two figures dominate. They sit near each other in the famous photograph taken on the conference steps, a photograph that has become iconic, capturing the moment physics split into two camps. On one side, Albert Einstein, 48 years old, already a legend, the man who revolutionized physics not once but multiple times. Special relativity in 1905. The photon, the quantum of light, also in 1905. General relativity in 1915, rewriting gravity itself. The man who proved atoms exist, who showed that space and time are woven together, who demonstrated that energy and mass are equivalent. Einstein arrives in Brussels with a mission. He is determined to destroy quantum mechanics, or at least the Copenhagen interpretation championed by his opponent, that opponent, Niels Bohr. 42 years old, Danish, professor at Copenhagen, where he has built an institute that attracts the brightest young minds in physics. Bohr is the godfather of quantum theory, the man who explained the atom in 1913, who proposed the principle of complementarity, who insists that quantum mechanics is complete, correct, and represents a fundamental revolution in how we understand reality. The two men are friends. They respect each other deeply. Einstein calls Bohr the Oracle of Copenhagen. Bohr admires Einstein's genius, his boldness, his willingness to question everything. But they disagree about the most fundamental question in science. What is reality? Does the universe exist independently of observation, obeying deterministic laws we can discover? Or is reality fundamentally probabilistic, observer-dependent, knowable only through measurement? Einstein believes in the former. Bohr champions the latter. The conference officially begins with presentations, but the real action happens in the hotel corridors, at breakfast, late into the night. Einstein corners Bohr with thought experiments designed to expose contradictions in quantum mechanics. Bohr, often joined by Heisenberg or Pauli, stays up until dawn working out responses. Each morning, Einstein presents a new challenge. Each afternoon, Bohr delivers a solution, back and forth, thrust and parry, like a chess match played by grandmasters. But this is not just intellectual sport. The stakes are profound. If Einstein is right, quantum mechanics is incomplete, a temporary approximation awaiting a deeper theory. If Bohr is right, the universe is stranger than anyone imagined. Reality itself depends on observation. Determinism is an illusion, and physics can never tell us what exists, only what we can measure. By the conference's end, most attendees side with Bohr. The Copenhagen interpretation becomes dominant, shaping physics for decades. But Einstein never surrenders. For the remaining 28 years of his life, he continues arguing, refining his objections, insisting that God does not play dice. Bohr, equally stubborn, defends his interpretation until his death in 1962. The debate between these two titans spans 3 decades, from 1927 to Einstein's death in 1955. It encompasses thought experiments of breathtaking cleverness, philosophical arguments of profound depth, and personal exchanges that reveal the humanity behind the physics. And remarkably, the debate is not settled. Nearly a century later, physicists still argue about the interpretation of quantum mechanics. New theories, many worlds, pilot wave, objective collapse, compete for acceptance. Experiments probe ever more deeply into the quantum realm, testing the boundaries of what Bohr and Einstein debated. To understand this greatest of scientific controversies, we must journey back to the beginning, to how quantum mechanics emerged, why it troubled Einstein so deeply, and what Bohr saw that Einstein could not accept. Let's start with the young Einstein, the revolutionary who helped birth quantum theory before he became the elder statesman fighting against it. So, as you settle into stillness tonight, imagine that room in Brussels, the greatest minds of an era gathered to understand the smallest scales of nature, friendships strained by intellectual honesty, revolutions unfolding in real time. 2 men, both giants, both brilliant, standing on opposite sides of a chasm neither can cross, and between them the question that haunts physics still: what is real? Let's explore how we arrived at this moment, and why the answer matters more than you might imagine. Chapter 2: The Revolutionary. Young Einstein and the birth of quantum theory. Here is a paradox. Albert Einstein helped create quantum mechanics, then spent the rest of his life trying to demolish it. To understand why, we must meet young Einstein, not the white-haired icon of later years, but the 26-year-old patent clerk in Bern, Switzerland, writing papers that would change the world. The year is 1905, Einstein's miracle year. In a single extraordinary burst of creativity, he publishes 4 papers, each worthy of a Nobel Prize. The first explains Brownian motion, the jittery dance of pollen grains in water, as evidence that atoms are real, finally settling a century-old debate. The second introduces special relativity, showing that space and time are relative, that simultaneity depends on the observer, that nothing can travel faster than light. The third derives E equals mc squared, revealing that energy and mass are interchangeable. But it's the paper between the second and third that concerns us tonight. Published in March 1905, titled "On a Heuristic Point of View, concerning the production and transformation of light. In this paper, Einstein proposes something radical. Light, which everyone knows is a wave, proved by interference, diffraction, all the elegant experiments of the 19th century, might also behave as if it's made of particles, discrete packets of energy, later called photons. Why would Einstein suggest something so seemingly contradictory? He was trying to explain the photoelectric effect, a puzzle that had stumped physicists for years. Shine light on a metal surface and electrons are ejected. Increase the light's intensity and you'd expect the electrons to come out with more energy, like waves crashing harder on a shore. But that's not what happens. The electron's energy depends only on the light's frequency, not its intensity. Bright red light ejects no electrons. Dim violet light does. Classical wave theory cannot explain this. But Einstein showed that if light comes in quanta, particles of energy proportional to frequency, the photoelectric effect makes perfect sense. Each photon carries energy, E equals hf, where f is frequency and h is Planck's constant. A high-frequency photon has enough energy to knock an electron free. A low-frequency photon does not, no matter how many you shine. This was revolutionary. Light as particles? It contradicted everything physicists thought they knew. Max Planck, who had introduced the constant h in 1900 to solve the blackbody radiation problem, initially regarded his own quantum of action as a mathematical trick, not physical reality. When Einstein took it seriously, suggesting light was genuinely quantized, Planck was skeptical. Niels Bohr, hearing of Einstein's light quantum in 1913, actively opposed it. He thought the idea was wrong, a step backward. It wasn't until 1925, 20 years later, that Bohr fully accepted the photon, but Einstein was right. Experiments confirmed the photoelectric effect exactly as he predicted. In 1921, Einstein received the Nobel Prize, not for relativity, which was still controversial, but for explaining the photoelectric effect. Yet here's the irony. Einstein's light quantum was one of the seeds that grew into quantum mechanics, the theory he would later reject. In 1913, Niels Bohr applied quantum ideas to the atom. He proposed that electrons orbit the nucleus in discrete energy levels, jumping between them by absorbing or emitting photons. Bohr's model explained the hydrogen spectrum beautifully, but it was ad hoc, a patchwork of classical orbits and quantum jumps. Through the 1910s and early 1920s, physicists struggled to build a coherent quantum theory. The old quantum theory, as it's now called, worked for some problems, but failed for others. It was clear something fundamental was missing. Then, in 1925 and 1926, the breakthrough arrived. Not from one person, but from several, working almost simultaneously. Werner Heisenberg in 1925 developed matrix mechanics, a strange algebraic formalism where observables like position and momentum became matrices that didn't commute. Max Born and Pascal Jordan helped refine it. Erwin Schrödinger in 1926 derived wave mechanics, representing particles as wave functions satisfying a differential equation, the Schrödinger equation. His approach seemed more intuitive, more visualizable than Heisenberg's matrices. It was soon proved that the two formalisms were mathematically equivalent, different languages describing the same theory. But what did the theory mean? What did the wave function represent? Max Born proposed an answer. The wave function's square gives the probability of finding a particle at a given location. Quantum mechanics doesn't predict where a particle is, only the likelihood of finding it somewhere when you measure. This was disturbing. Classical mechanics is deterministic. Given a particle's position and momentum, you can calculate its future trajectory precisely. But quantum mechanics says you cannot know both position and momentum precisely. The uncertainty principle, formulated by Heisenberg in 1927. And even if you could, the theory gives only probabilities. Einstein was troubled. He had helped ignite the quantum revolution with his photon. But the direction it was taken, indeterminism, probability, the primacy of measurement, violated his deepest intuitions about how nature works. He famously wrote to Max Born in 1926, "Quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a great deal but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice. By the old one, Einstein meant God, or nature, or the fundamental structure of reality. He believed the universe operates according to deterministic laws. Randomness, he thought, reflects our ignorance, not a fundamental feature of nature." Bohr disagreed. At the 1927 Solvay conference, he presented the Copenhagen interpretation, which would become the orthodox view. According to Bohr, quantum mechanics is complete. The wave function describes everything that can be known. Asking what a particle is doing before you measure it is meaningless. A question without an answer, like asking what happened before time began. This was too much for Einstein. He could not accept that reality depends on observation, that the moon isn't there when no one looks, and so, at that conference in Brussels, the battle began. As you rest, imagine the young Einstein, bold, confident, willing to overturn centuries of physics with a single paper. He trusted his intuition, his sense of how nature should be, but now that intuition is leading him into opposition with a new generation, with a theory his own work helped create. The revolutionary becomes the conservative, the iconoclast becomes the skeptic. It's a pattern repeated throughout science. Today's rebels become tomorrow's guardians of orthodoxy. Einstein, who dared to challenge Newton, now finds his own ideas challenged by Bohr. Who was right? Let's meet the other side of the debate, Niels Bohr and his quantum wonderland. Chapter 3. The Oracle, Bohr and the Copenhagen Interpretation. Niels Bohr was not a mathematical prodigy like Einstein or Heisenberg. He was a thinker, slow, deliberate, wrestling with ideas until he understood them deeply. Born in Copenhagen in 1885, Bohr studied physics at the University of Copenhagen, then moved to England to work with J.J. Thomson at Cambridge and Ernest Rutherford at Manchester. It was in Manchester, in 1913, that Bohr made his first great contribution. Rutherford had discovered that atoms have nuclei, tiny dense cores containing most of the atom's mass. But this created a problem. Electrons, orbiting the nucleus like planets around the sun, should radiate energy continuously and spiral inward, collapsing in a fraction of a second. Atoms should be unstable, yet they're not. Bohr proposed a radical solution. Electrons occupy discrete energy levels. They don't radiate while in these levels. They only emit or absorb energy when jumping between levels. The energy of the emitted or absorbed light equals the difference between levels. This explained why hydrogen emits light at specific wavelengths. The Balmer series, the Lyman series, frequencies that had been measured but not understood. Bohr's model was a triumph, but also a puzzle. Why are energy levels quantized? Why don't electrons radiate in orbits? Bohr had no deeper explanation. He imposed these rules by fiat, justified by experiment but lacking theoretical foundation. Still, the model established Bohr as a leader in quantum physics. In 1920, he founded the Institute for Theoretical Physics in Copenhagen, which quickly became the world's centre for quantum research. Young physicists flocked there: Heisenberg, Pauli, Dirac, many others, drawn by Bohr's insight and encouragement. Bohr had a unique working style. He would pace, dictating to an assistant, often revising the same sentence dozens of times, searching for exactly the right words. His papers are famously dense, written in a style that emphasizes nuance and complementarity, avoiding definitive claims. This reflected Bohr's philosophy. He believed physics should describe what we can observe and measure, not speculate about hidden realities we cannot access. When quantum mechanics was formalized in 1925 to 1926, Bohr embraced it fully. He saw it not as an incomplete approximation, but as a fundamental shift in how we think about nature. The core of Bohr's interpretation is complementarity, the idea that particles exhibit mutually exclusive properties depending on how you measure them. An electron can behave as a particle or a wave, but never both simultaneously. Position and momentum are complementary. Measuring one precisely makes the other uncertain. This isn't a limitation of our instruments, Bohr argued, it's intrinsic to nature. Quantum systems don't have definite properties until measured. The act of measurement brings properties into existence. Bohr also emphasized the role of classical concepts. We can only describe quantum phenomena using the language of classical physics, position, momentum, energy, because these are the concepts our macroscopic measuring devices embody. But quantum systems don't obey classical logic. We're forced to use classical language to describe fundamentally non-classical behavior, which is why quantum mechanics seems paradoxical. At the 1927 Solvay conference, Bohr presented these ideas. He discussed the double-slit experiment, light or electrons passing through two slits creating an interference pattern, proving wave behavior. But if you try to detect which slit the particle goes through, the interference vanishes and you see particle behavior. Bohr said this demonstrates complementarity. Wave and particle descriptions are both valid but cannot coexist. The experimental setup determines which aspect appears. Einstein listened politely. Then, during breaks, over meals, late into the night, he began his assault. He devised thought experiments designed to show that quantum mechanics leads to contradictions, or allows you to measure position and momentum simultaneously, violating the uncertainty principle. One of Einstein's early challenges involved the double-slit experiment itself. He imagined mounting the screen with the two slits on a delicate apparatus that could measure the recoil when a particle passes through. If the particle goes through the top slit, the screen recoils downward. If through the bottom slit, it recoils upward. By measuring the recoil, you could determine which slit the particle used while still seeing the interference pattern. Bohr thought about this overnight. By morning, he had the answer. To measure the screen's recoil precisely enough to tell which slit was used, you must know the screen's initial position with great accuracy. But by the uncertainty principle, this makes the screen's momentum uncertain. That momentum uncertainty gets transferred to the particle, introducing enough position uncertainty to wash out the interference pattern. Einstein's cleverness was matched by Bohr's. The uncertainty principle holds, complementarity stands. Einstein tried again. At the 1930 Solvay conference, he presented the photon box thought experiment, perhaps his most ingenious challenge. Imagine a box containing radiation. The box has a shutter controlled by a clock. At a precise time, the shutter opens briefly, releasing a single photon. You can weigh the box before and after. The mass change via E = mc² tells you the photon's energy. The clock tells you when it was released. You've measured energy and time simultaneously, violating the time-energy uncertainty relation. Bohr was reportedly shaken. He walked around looking unhappy, as Leon Rosenfeld recalled. He muttered, argued with himself, couldn't find the flaw. Then, in the middle of the night, inspiration struck. Bohr realized, to weigh the box precisely, you must use a gravitational field. In a gravitational field, time runs differently at different heights. Einstein's own general relativity predicts this. The mass change shifts the box vertically in the gravitational field, introducing a time uncertainty proportional to the energy uncertainty. Einstein's thought experiment doesn't violate the uncertainty principle. It confirms it, using Einstein's own theory of relativity. When Bohr presented this solution, Einstein conceded the point. It's said that he even smiled, appreciating the elegance of being beaten by his own relativity. But Einstein wasn't done. He shifted tactics. He stopped trying to prove quantum mechanics wrong or self-contradictory. Instead, he argued it was incomplete. It worked, but there must be a deeper theory underneath, one that restores determinism and objective reality. This led to the EPR paper, which we'll explore in a later chapter. But first, let's understand the philosophical divide between Einstein and Bohr more deeply. As you settle into rest, picture Bohr pacing his office in Copenhagen, dictating, revising, searching for the right words to describe a reality that defies words. He sees quantum mechanics not as a failure of human understanding, but as a revelation. Nature is fundamentally different from what we assumed. We must let go of classical intuitions, determinism, objectivity, the idea that things exist independently of observation. Einstein cannot let go. He believes there's a reality out there, governed by laws, existing whether we observe it or not. Two brilliant minds, two incompatible worldviews. One will shape the future of physics, the other will haunt it, whispering doubts that persist to this day. Let's now turn to the thought experiments that defined their battle. A war waged not with equations but with imagination. Chapter 4. The Thought Experiments. Chess played with photons and atoms. Physics is often imagined as a realm of equations and experiments, but some of its most profound battles have been fought in the mind, through thought experiments, Gedanken experiments as Einstein called them. A thought experiment is a scenario designed to probe the consequences of a theory, not through actual measurement but through careful reasoning. They're powerful because they strip away practical limitations. You can imagine perfect measurements, ideal conditions, systems isolated from all disturbance. Einstein was a master of the thought experiment. He imagined riding alongside a light beam, leading to special relativity. He pictured an accelerating elevator in empty space, indistinguishable from gravity, leading to general relativity. Now he turned this skill against quantum mechanics. Let's walk through the most famous thought experiments from the Einstein-Bohr debates, understanding not just the physics, but the deeper clash of philosophies each represents. Einstein's first major challenge at the 1927 Solvay conference was actually a refinement of the classic double-slit experiment. In the standard setup, electrons or photons pass through two slits and create an interference pattern on a screen. This proves they're waves. Only waves interfere. But if you try to detect which slit a particle goes through, the interference vanishes. Now the particle behaves classically. Bohr explained this via complementarity. Wave and particle are complementary descriptions. The experimental setup determines which you see. Trying to measure the path, particle behavior, destroys the interference, wave behavior. Einstein thought this was too convenient. He designed a variation. Mount the screen with the slits on a movable apparatus so delicate it can measure the recoil when a particle passes through. If a particle goes through the top slit, it imparts momentum to the screen in one direction. Bottom slit, opposite direction. Measuring this recoil tells you which slit was used, but the particle still hits the far screen, potentially contributing to an interference pattern. If this works, Einstein argued, you get both: path information, particle, and interference, wave, simultaneously, violating complementarity. Bohr's response, developed overnight, was subtle and powerful. To measure the screen's recoil precisely enough to distinguish which slit the particle used, you need to know the screen's initial momentum with great accuracy. By the uncertainty principle, delta x delta p greater than or equal to h bar over 2, this means the screen's position becomes uncertain. That position uncertainty affects where the slits are located. The slits' positions become fuzzy. This introduces just enough uncertainty in the particle's path to wash out the interference pattern. You can choose: measure the recoil, gaining path information, losing interference, or don't measure it, preserving interference, losing path information. But you cannot have both. Complementarity holds. The uncertainty principle, far from being violated, is precisely what enforces complementarity. Einstein acknowledged the cleverness, but wasn't satisfied. He moved on to more sophisticated challenges. 3 years later, at the 6th Solvay conference, Einstein presented what many consider his most brilliant thought experiment. Imagine a box filled with electromagnetic radiation. The box has a shutter controlled by a clock inside. At a predetermined time, the shutter opens briefly, just long enough to release a single photon, then closes. Before and after the photon escapes, you weigh the box. The mass difference via E equals mc squared gives the photon's energy with arbitrary precision. The clock gives the time of emission with arbitrary precision. But quantum mechanics says energy and time satisfy an uncertainty relation. Delta E delta t greater than or equal to h bar over 2. If you know the time precisely, delta t approximately 0, the energy must be completely uncertain. If you know the energy precisely, delta E approximately 0, the time must be completely uncertain. Einstein's thought experiment seems to violate this. You get both energy and time precisely. Bohr, as witnesses reported, was deeply troubled. He couldn't immediately find the error. He spent hours pacing, muttering, looking unhappy, unusual for Bohr, who was normally calm and confident. Then, overnight, Bohr found the answer, and it was beautiful. To weigh the box precisely, you must measure its position in a gravitational field. You attach the box to a spring scale, note its equilibrium position, then note how the position changes after the photon escapes. But here's the twist. The box is in a gravitational field. General relativity, Einstein's own theory, says that time runs at different rates at different gravitational potentials. The higher you are, the faster time flows. When the photon escapes, the box becomes lighter, and the spring scale shifts the box vertically. This vertical shift changes the box's gravitational potential, which changes the rate at which the clock inside the box runs. To measure the box's mass, and thus the photon's energy, with precision delta E, the box's vertical position must be uncertain by delta Z. This uncertainty in position means uncertainty in gravitational potential, which means uncertainty in the clock's rate, which means uncertainty in the time delta t. Bohr showed that the resulting uncertainties satisfy exactly delta E delta t greater than or equal to h bar over 2. Einstein's own general relativity enforces the uncertainty principle he was trying to disprove. When Bohr presented this, Einstein reportedly smiled and said something to the effect of, "You got me." He never again tried to disprove the uncertainty principle directly. But this wasn't surrender. Einstein shifted strategy. By 1935, Einstein had stopped trying to prove quantum mechanics internally contradictory. Instead, he argued it was incomplete, a correct but partial description, missing something deeper. In May 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It's known as the EPR paper from the author's initials. The argument is subtle, but here's the essence. Imagine two particles that interact and then separate, flying far apart, say, light years. Quantum mechanics describes them as entangled. Their properties are correlated in a way that can't be explained by each particle having independent properties. For example, two electrons might be in a state where their total spin is zero. If you measure one electron's spin along the z-axis and find up, the other electron's spin along the z-axis must be down. If you find down, the other must be up. But here's the twist. Quantum mechanics says that before measurement, neither electron has a definite spin. The act of measuring the first electron's spin causes both spins to become definite. Einstein found this absurd. The electrons are far apart, light years if you like. How can measuring one instantly affect the other? This seems to require faster-than-light influence, violating relativity. EPR proposed two alternatives. 1. Quantum mechanics is wrong. There are no such correlations. 2. Quantum mechanics is incomplete. The particles had definite spins all along, determined by some hidden variables we don't yet understand. EPR argued for option 2. They defined a criterion for reality. If, without disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of reality corresponding to that quantity. By measuring the first electron's spin, you can predict the second electron's spin with certainty, without touching the second electron. Therefore, the second electron's spin must be real, determined before measurement. Quantum mechanics, which says the spin is indefinite until measured, is incomplete. This argument is compelling, resting on what seems like common sense, that reality is local, no faster than light influences, and objective. Things have properties before measurement. Bohr's response, published a few months later, is famously difficult to understand. He argued that EPR's criterion for reality is too naive. You cannot talk about the second electron's spin independently of the measurement setup used on the first electron, even though the electrons are far apart. This sounds bizarre. How can a measurement here affect the reality of something there? But Bohr insisted this is precisely what quantum mechanics reveals. Properties like spin don't exist independently of measurement context. Most physicists at the time sided with Bohr, but Einstein wasn't convinced. He spent the rest of his life refining his objections, writing letters to colleagues, insisting that quantum mechanics must be incomplete. So, as you drift tonight, picture these thought experiments, not as dry physics puzzles, but as dramas of the mind, where Einstein and Bohr probe the nature of reality itself using only imagination and logic. The double slit reveals complementarity. The photon box shows how relativity enforces uncertainty. And EPR introduces entanglement, the strangest feature of quantum mechanics, the one that Einstein called spooky action at a distance. These aren't just historical curiosities. They're windows into the deep structure of nature, questions that remain open, mysteries that still inspire wonder and debate. Now let's explore the philosophical chasm that underlies these thought experiments, the clash between realism and anti-realism, determinism and indeterminism, the battle for the soul of physics. Chapter 5. The Philosophical Chasm. What is real? At its deepest level, the Einstein-Bohr debate is not about mathematics or experiments. It's about philosophy, specifically about the nature of reality and what physics can tell us about it. Two questions sit at the heart of their disagreement. 1. Does reality exist independently of observation? 2. What is the purpose of a physical theory? Einstein and Bohr gave profoundly different answers. Einstein was a realist. He believed in an objective reality, a universe that exists out there, independent of whether anyone observes it. This seems obvious, almost trivial. Of course, the moon is there when no one looks. Of course, atoms have definite positions and momentia, even when we're not measuring them. Reality doesn't depend on us. But Einstein's realism went deeper than common sense. It was rooted in a particular view of what physics should achieve. For Einstein, the goal of physics is to describe nature as it truly is, to uncover the laws governing reality, to reveal the hidden mechanisms behind phenomena. A theory isn't just a tool for predicting measurements, it's a representation of objective truth. Einstein expressed this beautifully in a 1949 essay. Physics is an attempt conceptually to grasp reality as it is thought independently of its being observed. In this sense, one speaks of physical reality. This view is called scientific realism. It holds that successful scientific theories refer to real entities and that the universe has a structure independent of our knowledge of it. Einstein also believed in determinism. He thought the universe evolves according to strict causal laws. Randomness, probability, uncertainty. These reflect our ignorance, not a fundamental feature of nature. This is why he said, God does not play dice. He wasn't being literal about God. He meant that nature at its deepest level is lawful and deterministic, not random. When quantum mechanics introduced indeterminism, saying that outcomes of measurements are genuinely random, not determined by prior states, Einstein rejected it. He believed quantum mechanics was a statistical theory, like thermodynamics, useful but incomplete. Beneath the probabilities there must be a deterministic reality governed by hidden variables. Bohr's position is harder to characterize. He's often called an anti-realist, but that's oversimplified. Bohr didn't deny that the world exists. He denied that we can meaningfully talk about what exists independently of how we measure it. For Bohr, the purpose of physics is not to describe reality as it is in itself. Physics describes phenomena, what we observe and can communicate about. Asking what a particle is really doing before measurement is, in Bohr's view, a meaningless question. Bohr emphasized the role of measurement apparatuses, which are macroscopic and classical. We can only describe quantum systems using classical concepts: position, momentum, energy, because these are the concepts our measuring devices embody. But quantum systems don't obey classical logic. This led Bohr to complementarity, the idea that certain properties are mutually exclusive. A particle can behave as a wave or as a particle, depending on the experimental setup, but not both simultaneously. Bohr also stressed that the act of measurement is not a passive observation. It's an interaction that fundamentally affects the system. You cannot separate the observer and the observed. This sounds like idealism, the philosophical view that reality depends on mind. But Bohr resisted that label. He wasn't saying reality is created by consciousness. He was saying that properties like position or momentum don't exist as independent facts until measurement brings them into existence through the interaction of quantum system and classical apparatus. Some historians argue Bohr was a pragmatist, not an anti-realist. He didn't care whether hidden realities exist because they are inaccessible. Physics should focus on what can be measured and predicted, not speculate about unknowables. Einstein and Bohr's disagreement wasn't just technical. It was a clash of deeply held convictions about how the world works and what science should do. Einstein wanted a theory that told him what is. Bohr offered a theory that told him what he could measure. Einstein sought deterministic laws. Bohr embraced fundamental randomness. Einstein believed in separability, that spatially separated systems have independent realities. Bohr denied this, pointing to entanglement. The two men could barely communicate. Einstein would say, "But the moon is there when I'm not looking." Bohr would reply, "Asking whether the moon exists when no one looks is a meaningless question. We can only talk about the moon in the context of observing it." This exasperated Einstein. It felt like wordplay, like evasion. He wanted straightforward answers. Does the moon exist or not? Bohr thought Einstein was clinging to outdated classical intuitions. Quantum mechanics forces us to revise what we mean by exists, by reality, by knowledge. It's not that the moon doesn't exist, it's that existence is subtler than classical physics assumed. Philosophers distinguish between epistemology, the study of knowledge, and ontology, the study of what exists. Einstein was primarily an ontologist. He wanted to know what really exists, what the universe is made of, what laws govern it. Bohr was primarily an epistemologist. He wanted to understand what we can know, how measurements work, what information can be extracted from experiments. This divide is still central to debates about quantum mechanics. Some interpretations, like pilot wave theory, de Broglie-Bohm, side with Einstein, restoring determinism and objective reality by adding hidden variables. Others, like the many worlds interpretation, avoid measurement-induced collapse but embrace a radical ontology. Every quantum outcome occurs, each in a separate branch of reality. Still others, like quantum Bayesianism, cubism, follow Bohr in treating quantum mechanics as a tool for updating beliefs, not describing objective reality. And experimentalists following the Copenhagen tradition often say, "Shut up and calculate. Don't worry about philosophy. Quantum mechanics works, use it." But Einstein believed philosophy matters. The questions, what is real and what can we know, aren't distractions, they're central to understanding nature. Who was right? That's the question that haunts physics, and remarkably, it's still open. In the 1960s, physicist John Bell proved a theorem that allows testing whether hidden variables can explain quantum correlations. Experiments, starting with the Lion aspect in the 1980s and refined by John Clauser and Anton Zeilinger, who won the 2022 Nobel Prize, have repeatedly confirmed quantum mechanics predictions and ruled out local hidden variables. Einstein's local realism is wrong. The universe does exhibit spooky action at a distance. Entanglement is real. But that doesn't mean Bohr was entirely right either. Bell himself was sympathetic to pilot wave theory, which is deterministic but non-local. Other interpretations remain viable. The debate Einstein and Bohr began continues, unresolved at the frontiers of physics. As you rest tonight, let this philosophical divide settle gently into your thoughts. Two brilliant minds, two incompatible visions of reality, both grappling with the same experimental facts. Einstein wanted the universe to make sense on human terms, objective, deterministic, comprehensible. Bohr said the universe doesn't owe us that. We must accept it on its own terms, however strange. Perhaps both were partly right. Perhaps reality is richer than either imagined. Now let's turn to a different dimension of their relationship, the personal friendship that survived the intellectual battle. If you're still with me on this journey through the greatest debate in physics, you're part of something rare. Minds willing to sit with deep questions, to explore mysteries that have no easy answers. A quick subscribe helps others discover this contemplative exploration where science, philosophy, and wonder converge. Now let's continue into the human story behind the physics, the friendship that endured despite profound disagreement. Chapter 6. The Friendship. Respect across the divide. Science is often portrayed as impersonal, a quest for objective truth where personalities don't matter. But the Einstein-Bohr debate reminds us that science is profoundly human, shaped by friendships, rivalries, and the messy reality of brilliant people trying to understand the universe while navigating their own egos and emotions. What's remarkable about Einstein and Bohr is that despite decades of profound disagreement, they remained friends. They respected each other deeply, genuinely enjoyed each other's company, and acknowledged each other's genius, even as they battled over the foundations of physics. Einstein and Bohr first met in 1920 when Einstein visited Copenhagen. Bohr gave a lecture, and afterward the two men walked and talked for hours. They discussed relativity, quantum theory, the nature of physical reality. Both were impressed. Einstein called Bohr a first-rate thinker, someone whose ideas, even when wrong, were always interesting. Bohr admired Einstein's boldness, his willingness to challenge conventional wisdom, his deep physical intuition. In the early 1920s, before quantum mechanics was fully developed, they were allies of a sort, both grappling with the mysteries of the quantum world, both dissatisfied with the old quantum theory's patchwork character. It wasn't until 1927, when the Copenhagen interpretation crystallized, that they found themselves on opposite sides. At the 1927 Solvay conference, their debates were intense but cordial. Paul Ehrenfest, a close friend of both, described the atmosphere in a letter. It was delightful for me to be present during the conversations between Bohr and Einstein, like a game of chess. Einstein all the time with new examples, Bohr from out of philosophical smoke clouds constantly searching for the tools to crush one example after the other. Heisenberg recalled that the debates were like a duel between two swordsmen of equal strength. Einstein would present a challenge. Bohr, sometimes with help from Heisenberg or Pauli, would work through the night to find the flaw. The next morning, Bohr would explain his solution, and Einstein would listen, nod, and then try another angle. There was no animosity. Both men were genuinely trying to understand the truth, using each other as intellectual sparring partners. After the conference, Einstein wrote to Ehrenfest, "I admire Bohr's sharp mind, but I remain convinced that God does not play dice." Bohr, for his part, said, "Einstein's objections are not meant to criticize quantum mechanics as such, but to find the point where the quantum mechanical description must be supplemented by a deeper theory." In other words, Bohr understood that Einstein wasn't being stubborn or foolish. Einstein was pursuing a different vision of what physics should achieve. When Einstein presented the photon box thought experiment in 1930, Bohr was visibly shaken. This was the closest Einstein came to defeating him. Witnesses report that Bohr looked unhappy, that he paced nervously, unable to immediately find the answer. For Bohr, who was usually confident and calm, this was unusual. But Einstein wasn't gloating. He genuinely wanted to know if he'd found a flaw in quantum mechanics. He respected Bohr enough to wait for a serious response. When Bohr delivered his solution the next day, using general relativity to show that the uncertainty principle holds, Einstein smiled. Some accounts say he even laughed. He appreciated the elegance of being beaten by his own theory. This is the mark of a true scientist, valuing truth over ego. Einstein could have sulked, could have tried to find another loophole. Instead, he acknowledged Bohr's cleverness and moved on to refining his arguments. The 1935 EPR paper marked a shift. Einstein stopped trying to prove quantum mechanics wrong and started arguing it was incomplete. Bohr's response to EPR was his most strained. His paper is famously difficult to understand, dense, repetitive, circling the issue without quite landing on a clear refutation. Some historians think Bohr was frustrated. EPR had touched a nerve, raising questions Bohr couldn't easily dismiss. The paper forced him to clarify his position, and he struggled to do so in a way that satisfied everyone. Einstein, reading Bohr's response, remained unconvinced. He wrote to Schrödinger, "Bohr's opinion about radiation is of interest, but I should not want to be forced into abandoning strict causality without defending it more strongly than I have so far. I find the idea quite intolerable that an electron exposed to radiation should choose of its own free will not only its moment to jump off, but also its direction." Notice the language: free will, intolerable. For Einstein, quantum indeterminism felt like giving up on understanding, like saying nature is fundamentally irrational. After 1935, Einstein and Bohr rarely met in person. Einstein was in Princeton at the Institute for Advanced Study, increasingly isolated from mainstream physics. Bohr remained in Copenhagen, continuing to develop quantum mechanics and its applications. But they continued corresponding through letters and mutual acquaintances. In 1948, Einstein wrote a long essay for a volume honoring his 70th birthday, explaining his philosophical objections to quantum mechanics. Bohr wrote a response, trying once more to explain complementarity. Reading their exchanges, you sense a sadness. Two old friends, each convinced the other is missing something fundamental, unable to bridge the gap. Einstein died in 1955. Bohr lived until 1962. After Einstein's death, Bohr spoke of him with great warmth, calling him the most profound thinker he had known. What can we learn from the Einstein-Bohr relationship? First, that profound intellectual disagreement need not destroy respect or friendship. They disagreed about the most fundamental questions in physics, but they never doubted each other's sincerity or brilliance. Second, that science progresses through such debates. The Einstein-Bohr controversy forced both sides to sharpen their arguments, to explore the implications of quantum mechanics more deeply. Even though Bohr won in the sense that the Copenhagen interpretation became dominant, Einstein's challenges led to important insights. EPR inspired Bell's theorem, which in turn led to modern quantum information theory. Third, that humility is essential. Both men were willing to admit when they didn't know something, to revise their views when presented with strong arguments. Einstein conceded the photon box. Bohr struggled with EPR. Neither pretended to have all the answers. So, as you drift into stillness, imagine these two giants, Einstein and Bohr, walking together in Copenhagen or Princeton, arguing about the moon and observation, laughing at the absurdity of a universe that defies common sense. They were opponents in the arena of ideas, but allies in the quest for truth. They showed that science, at its best, is a cooperative endeavor, even when cooperation looks like conflict. Now, let's turn to the decisive test, the experiments that determined who was right. Chapter 7. The Verdict: Bell's Theorem and the Death of Local Realism. For decades, the Einstein-Bohr debate remained philosophical. Both sides had strong arguments, but no experiment could decisively settle the question. Quantum mechanics made accurate predictions, but did that prove it was complete? Or could there be a deeper theory, with hidden variables, that gave the same predictions while restoring Einstein's realism? In 1964, a physicist named John Stuart Bell changed everything. He proved a theorem that allowed the debate to be tested experimentally. John Bell was not a household name like Einstein or Bohr. He worked at CERN, the European Particle Physics Laboratory, and his main job was accelerator physics. But in his spare time, he thought deeply about the foundations of quantum mechanics. Bell was troubled by the Copenhagen interpretation. Like Einstein, he felt that quantum mechanics' refusal to describe reality was unsatisfying. He was particularly interested in pilot wave theory, developed by Louis de Broglie and later refined by David Bohm. Pilot wave theory is deterministic. Particles have definite positions at all times, guided by a pilot wave that evolves according to the Schrödinger equation. The randomness of quantum mechanics arises from our ignorance of initial conditions, not from fundamental indeterminism. But pilot wave theory is non-local. The pilot wave connects distant particles instantly, creating correlations that seem to violate relativity's prohibition on faster-than-light influences. Einstein would have hated this. He wanted local hidden variables, a theory where distant events are independent, connected only by signals travelling at or below light speed. Bell asked, can local hidden variables reproduce quantum mechanics predictions? In 1964, Bell published a paper titled On the Einstein-Podolsky-Rosen Paradox. In it, he proved a stunning result. No theory based on local hidden variables can reproduce all the predictions of quantum mechanics. More specifically, Bell derived an inequality, now called Bell's inequality, that any local hidden variable theory must satisfy. Quantum mechanics violates this inequality. This means, if experiments confirm quantum mechanics' violations of Bell's inequality, Einstein's local realism is wrong. The universe cannot be both local and deterministic. Let's understand Bell's argument without too much mathematics. Consider two entangled particles, like the electrons in the EPR thought experiment. They're separated by a large distance. Alice measures her particles' spin along some axis. Bob measures his particles' spin along a different axis. If local hidden variables exist, the outcomes of Alice's and Bob's measurements should be determined by properties the particles carried with them when they separated. Alice's choice of measurement axis might affect her result, but it shouldn't affect Bob's result, because no signal can travel from Alice to Bob faster than light. Bell showed that this assumption, locality plus realism, leads to constraints on the correlations between Alice's and Bob's measurements. These constraints are expressed as inequalities. Quantum mechanics predicts correlations that violate these inequalities. Specifically, quantum entanglement produces stronger correlations than any local hidden variable theory allows. This was revolutionary. Bell had turned a philosophical debate into an experimental question. You could actually test whether the universe obeys local realism or quantum mechanics. In the 1970s and 1980s, physicists began testing Bell's inequality. The first was John Clauser, who in 1972 performed experiments with entangled photons. His results violated Bell's inequality, supporting quantum mechanics, but the experiments had loopholes. Critics argued that maybe the detectors were inefficient, missing some particles, or that subtle influences could still pass between the measurement stations. In 1982, Alain Aspect in France performed more sophisticated experiments, using rapidly changing measurement settings to close some loopholes. Again, Bell's inequality was violated. Quantum mechanics was confirmed. Over subsequent decades, Anton Zeilinger and others refined the tests, closing more loopholes, using satellites to separate the particles by thousands of kilometers, ensuring that no signal could possibly connect the measurements. Every experiment confirmed quantum mechanics. Bell's inequality is violated. Local hidden variables are ruled out. In 2022, Clauser, Aspect, and Zeilinger were awarded the Nobel Prize in Physics for their work. What does this mean? Bell's theorem and the experiments that confirmed it have profound implications. First, Einstein's vision of a local realism is wrong. The universe does not consist of particles with definite independent properties interacting only through local influences. Second, entanglement is real. Two particles can be correlated in ways that cannot be explained by any pre-existing properties they carry. Measuring one particle genuinely affects the other, instantly, regardless of distance. This is the spooky action at a distance Einstein rejected. It's now experimentally confirmed, but, and this is crucial, entanglement does not allow faster-than-light communication. You cannot use it to send messages. The correlations are statistical, revealed only when Alice and Bob compare their results. From Alice's perspective alone, her measurements look random. She can't tell whether Bob has measured his particle or not. So relativity is safe. No information travels faster than light. But the universe is non-local in a subtler sense. Measurement outcomes can depend on distant events in ways that defy classical explanation. Einstein was wrong, but not completely. It's tempting to say Einstein was wrong and Bohr was right, but that's oversimplified. Einstein was wrong about local hidden variables. The universe is not as he hoped. But Einstein's deeper concern that quantum mechanics might be incomplete is still debated. Some interpretations, like pilot wave theory, accept non-locality and restore determinism. Others, like many worlds, avoid collapse entirely. And Bell himself, who proved the theorem, was sympathetic to Einstein's discomfort with Copenhagen. He wrote, "I felt that Einstein's intellectual superiority over Bohr, in this instance, was enormous. A vast gulf between the man who saw clearly what was needed and the obscurantist. Bell thought Bohr's refusal to talk about reality was a cop-out. He preferred pilot wave theory, which says particles really do have positions, even if we can't measure them perfectly. So the verdict is mixed. Local realism is dead. But the debate over interpretation continues. Consider this. The greatest debate in physics was settled not by argument but by experiment. Nature itself weighed in, revealing a universe stranger than either Einstein or Bohr fully grasped. Entanglement is real. Particles separated by light years are connected in ways that transcend space. The universe is woven together by invisible threads. Einstein hated this. But nature doesn't care what we prefer. It simply is, mysterious, beautiful, and profoundly non-local. Now let's explore what this means for our understanding of reality, free will, and the nature of the cosmos. Chapter 8. Implications. What does it all mean? The Einstein-Bohr debate wasn't just about physics. It touched on philosophy, metaphysics, even theology. If quantum mechanics is correct, if the universe is fundamentally probabilistic and non-local, what does that mean for reality, causality, free will, and our place in the cosmos? Let's explore some of the profound implications. The death of determinism. classical physics was deterministic. Given the state of the universe at one moment, every particle's position and momentum, the laws of physics determine the state at every future moment. The universe unfolds like clockwork. This had philosophical consequences. If the universe is deterministic, then your actions are predetermined. Free will is an illusion. Everything you will ever do was set in motion at the Big Bang. Quantum mechanics breaks this chain. It introduces genuine randomness. When a radioactive atom decays, when a photon passes through a beam splitter, the outcome is not determined by prior states. It's fundamentally random, governed only by probabilities. Does this restore free will? That's debated. Some argue that quantum randomness is not freedom. Your choices being random is not better than them being predetermined. Others see quantum indeterminism as opening space for free will, especially if consciousness plays a role in collapsing the wave function, a controversial idea. What's clear is that the universe is not clockwork. The future is not written. Reality unfolds moment by moment, shaped by quantum chance. Bell's theorem and the experiments that confirmed it prove the universe is non-local. Entangled particles, even when separated by vast distances, remain connected in a way that defies classical explanation. This is weird. Relativity says nothing can travel faster than light. Yet entanglement seems to involve instantaneous correlations. How can both be true? The resolution is subtle. Entanglement doesn't transmit information faster than light. You cannot use it to send messages. The correlations are statistical, revealed only when you compare measurements, which requires classical communication at or below light speed. But ontologically, in terms of what exists, entanglement suggests that space is not as fundamental as we thought. Particles are not fully independent entities, even when separated. They're part of a larger whole, a quantum state that transcends spatial separation. Some physicists like Leonard Susskind and Juan Maldacena have explored connections between entanglement and spacetime geometry. They propose that spacetime itself might emerge from quantum entanglement, a radical idea still being developed. If true, it would vindicate Einstein in an unexpected way. He sought a unified understanding of space, time, and matter. Quantum entanglement might be the key. One implication of the Einstein-Bohr debate that's still unresolved is the measurement problem. Quantum mechanics describes systems as evolving in superposition, multiple possibilities coexisting, until measured. Measurement causes collapse, selecting one outcome. But what counts as measurement? Is it the interaction with a macroscopic device, the recording of a result, the awareness of a conscious observer? Copenhagen interpretation says, don't ask. Measurement is a primitive concept not analyzable further, but this is unsatisfying. It divides the universe into quantum systems, which are in superposition, and classical systems, which are definite. Where's the boundary? How do you explain the emergence of classicality from quantum rules? Several interpretations attempt to solve this. Many worlds. Interpretation. There's no collapse. Every outcome occurs, each in a separate branch of reality. Measurement doesn't select one outcome. It splits the universe into multiple copies, each experiencing a different outcome. Pilot wave theory. Particles always have definite positions guided by a pilot wave. Measurement reveals pre-existing properties, not causes collapse. Objective collapse theories. The wave function spontaneously collapses when systems reach a certain size or complexity, due to some physical mechanism, gravity for instance. None of these is universally accepted. The measurement problem remains open. Some interpretations of quantum mechanics give consciousness a central role. If observation causes collapse, and observation requires a conscious observer, then consciousness is fundamental to reality. This idea, championed by physicists like Eugene Wigner and John von Neumann, is controversial. Most physicists reject it, arguing that observation just means interaction with a macroscopic system, not awareness. But a few researchers still explore quantum consciousness theories, suggesting that the brain's neurons might exploit quantum effects and that consciousness might be a quantum phenomenon. This remains speculative, verging on philosophy of mind rather than physics, but it shows how the Einstein-Bohr debate touches on the deepest questions of existence. Is Bohr's pragmatism enough? Bohr's position that physics should describe what we can measure, not speculate about hidden realities, has been enormously successful. Quantum mechanics works. It's the foundation of modern technology, semiconductors, lasers, MRI, quantum computing. But is pragmatism enough? Should we be satisfied with a theory that predicts experiments but doesn't explain what's really happening? Einstein said no. He believed understanding means grasping the underlying reality. A theory that refuses to describe reality is incomplete, even if it makes perfect predictions. Many physicists today agree with Einstein's spirit, if not his specific objections. They want interpretations that tell us what's real, many worlds, pilot wave, objective collapse, not just what we'll measure. Others embrace Bohr's pragmatism, arguing that physics has always been about prediction and control, not metaphysical truth. This debate mirrors the original Einstein-Bohr split. It's still unresolved, still shaping how physicists think about their field. As you drift toward rest, let these implications settle gently. The universe is non-local, woven together by invisible threads. It's indeterministic, unfolding moment by moment in ways no one can predict. It's mysterious, refusing to fit into the neat boxes of classical logic. Einstein wanted the universe to make sense on human terms. Bohr said we must accept it on its own terms, however strange. Perhaps the lesson is humility. The universe doesn't owe us an intuitive explanation. It simply is, beautiful, baffling, endlessly surprising. Now, let's explore the modern legacy of the Einstein-Bohr debate, how it shapes physics, technology, and our quest to understand reality. Chapter 9. The Legacy: How the Debate Shapes Modern Physics. The Einstein-Bohr debate didn't end in 1955 when Einstein died, or in 1962 when Bohr passed away. It continues today, shaping research in quantum foundations, quantum information, and the search for a theory of everything. Let's explore how their intellectual battle echoes through modern physics. The quantum information revolution. In the 1980s and 1990s, physicists began thinking about quantum mechanics not just as a description of nature, but as a resource for information processing. Entanglement, which Einstein derided as spooky, turns out to be incredibly useful. It enables quantum teleportation, where the state of a particle can be transferred to another particle far away, using shared entanglement and classical communication. It enables quantum cryptography, where security is guaranteed by the laws of physics, not mathematical complexity. Eavesdropping on a quantum key distribution protocol disturbs the entanglement, revealing the eavesdropper's presence, and it enables quantum computing, where qubits in superposition perform calculations in ways classical bits cannot, potentially solving problems intractable for classical computers. All of these technologies exploit features of quantum mechanics that Einstein thought were problematic: superposition, entanglement, indeterminacy. The irony is rich. Einstein's EPR paper, meant to show quantum mechanics was incomplete, laid the groundwork for quantum information theory. By highlighting entanglement, EPR helped physicists realize its potential. Despite quantum mechanics' success, physicists still argue about what it means. The Copenhagen interpretation, championed by Bohr, remains widely taught, but many researchers find it unsatisfying. The many worlds interpretation, proposed by Hugh Everett in 1957, has grown in popularity, especially among cosmologists and quantum information theorists. It avoids the measurement problem by denying collapse. Every outcome occurs, each in a separate branch. Pilot wave theory, de Broglie-Bohm, which Einstein might have liked for its determinism, is taken seriously by a minority of physicists. It's experimentally equivalent to standard quantum mechanics, but provides a deterministic, realist picture. Objective collapse theories, where the wave function spontaneously collapses due to gravity or other mechanisms, are actively researched. These theories make testable predictions, differing slightly from standard quantum mechanics. And newer interpretations, like cubism, quantum Bayesianism, and relational quantum mechanics, offer fresh perspectives, treating the wave function as describing knowledge or relations rather than objective reality. The diversity of interpretations shows that Einstein's question, "What is quantum mechanics really telling us about reality?" is still open. Modern experiments continue probing the foundations of quantum mechanics, testing the limits of superposition, entanglement, and measurement. In 2019, researchers demonstrated quantum entanglement between thousands of atoms, approaching macroscopic scales. They're pushing toward Schrödinger's cat, a macroscopic system in superposition. In 2022, experiments tested whether quantum mechanics applies to gravity, looking for interference effect in particles moving through gravitational fields. And ongoing experiments test collapse theories, searching for deviations from standard quantum mechanics that might reveal where or how the wave function collapses. These experiments honor the spirit of the Einstein-Bohr debate, refusing to accept theory without question, probing its limits, seeking deeper understanding. One major unresolved issue is how to reconcile quantum mechanics and general relativity. General relativity describes gravity as the curvature of space-time. It's a classical theory, deterministic and smooth. Quantum mechanics describes matter and energy as probabilistic and discrete. Combining them, creating a theory of quantum gravity, has proven extraordinarily difficult. String theory, loop quantum gravity, and other approaches attempt this. Each has insights, but none is fully accepted. Interestingly, both Einstein and Bohr's perspectives are relevant here. Einstein sought a unified theory, a single framework encompassing all forces. Quantum gravity would be that theory. But Bohr's emphasis on complementarity and the limits of classical concepts might also be crucial. Perhaps space and time, like position and momentum, are complementary, only definable in certain contexts. The search for quantum gravity continues, driven by the same questions Einstein and Bohr debated. What is real? What can we know? How do we describe a universe that defies our intuitions? December 2025, the final evidence. Now, we arrive at the present. On December 8th, 2025, a team at the University of Science and Technology of China, USTC, published a result that Einstein would have found both beautiful and terrifying. They used the Jinan 1 satellite to perform a Bell test across 12,900 kilometers, but they added a 2025 twist. They used cosmic Bell settings. Instead of a computer choosing the detector settings, They pointed telescopes at two different ancient quasars on opposite sides of the observable universe. The light from these quasars, light that was emitted 10 billion years ago, determined how the 2025 detectors would measure the entangled particles. The data was finalized. The violation of Bell's inequality was recorded at a level of 50 standard deviations. To give you an idea of what that means in sleep-entangled terms, the odds of Einstein being right and this result being a fluke are roughly the same as winning the lottery every single day for the rest of your life. In these 2025 trials, the Jinan one achieved a secret key rate that was 100 times faster than anything seen in 2022. This isn't just a physics experiment anymore. It is the backbone of the 2026 quantum internet. We have moved from proving Bohr right to using his ghosts to carry our bank transactions and private messages. In the same month, MIT researchers used atom interferometry to finally answer Einstein's 1927 question about momentum transfer. They proved that you cannot even think about a particle having a path without destroying its quantum nature. This closed the final freedom of choice loophole. Unless the entire history of the universe was a conspiracy planned 10 billion years ago, there is no way the particles could have cheated. Bohr's complementarity, the idea that the observer and the observed are one single system, has been confirmed to 12 decimal places. The great duel has a winner. Niels Bohr's ghostly interconnected world is the world we live in. But as we shall see, Einstein's defeat has actually led us to the greatest technological revolution in human history. We don't live in a clockwork. We live in an entanglement. Beyond physics, the Einstein-Bohr debate offers lessons for how we pursue knowledge. First, the value of dissent. Einstein's refusal to accept Copenhagen orthodoxy forced the community to think harder, to clarify arguments, to test assumptions. Even though he was wrong about local hidden variables, his challenges led to deeper insights. Second, the importance of philosophical clarity. The debate wasn't just about experiments, it was about what the experiments mean, what we're trying to achieve with science. Philosophy matters. Third, humility. Both Einstein and Bohr were willing to revise their views when faced with strong arguments. Neither claimed to have final answers. And fourth, the role of friendship and respect. Science is a human endeavor. Ideas clash, but people needn't. Einstein and Bohr showed that profound disagreement can coexist with mutual admiration. As you settle into stillness, picture the legacy of their debate, rippling forward through time, shaping technologies that will define the 21st century, inspiring new generations of physicists to question, to probe, to wonder. Einstein and Bohr are gone, but their questions remain. What is real? What can we know? How should we describe a universe that's stranger than we ever imagined? These questions belong to us now, and perhaps, in the quiet of your own contemplation, you'll find your own answers, or at least your own way of living with the mystery. In our final chapter, let's reflect on what the Einstein-Bohr debate reveals about science, certainty, and the human quest for understanding. Chapter 10: The Unfinished Revolution, Living with Mystery. We've travelled a long journey tonight, from Brussels in 1927 to the cutting edge of modern quantum physics. We've met two giants of science, witnessed their intellectual battle, and explored the profound implications of their debate. Now, as we approach the end, let's reflect on what this greatest of physics controversies reveals about science, knowledge, and the human condition. One striking lesson from the Einstein-Bohr debate is that certainty is elusive. Even in physics, the most rigorous of sciences, physics deals with measurable, testable phenomena. It's grounded in mathematics, constrained by experiment. If any field can achieve certainty, surely it's physics. Yet here we are, nearly a century after quantum mechanics' birth, still arguing about what it means. The math is settled, the predictions are confirmed. But the interpretation, the question of what's really happening, remains contested. This doesn't mean physics is flawed or that truth is relative. It means that even in the hardest of sciences, philosophy intrudes. We can't escape questions about reality, knowledge, and meaning. Einstein wanted certainty. He wanted a theory that told him definitively what the universe is made of, how it works, why it exists. Bohr accepted uncertainty. He was comfortable saying, "Quantum mechanics tells us what we can measure, not what is." For Bohr, this was not a failure. It was a recognition of limits. Who was right? Perhaps both. Perhaps we should seek understanding while acknowledging that perfect certainty is impossible. The Einstein-Bohr debate also reminds us that science is done by people. Brilliant, flawed, stubborn people with egos, emotions, and biases. Einstein and Bohr were not dispassionate calculators. They were driven by deep convictions about how the universe should be. Einstein's belief in determinism and objective reality shaped his objections to quantum mechanics. Bohr's pragmatism and emphasis on measurement shaped his defense. Neither was entirely objective. Both were influenced by philosophical commitments formed early in life. This doesn't invalidate their work, it humanizes it. Science progresses not through pure logic, but through a messy process of argument, experiment, revision, and occasional stubbornness. The best scientists like Einstein and Bohr are aware of their biases and try to compensate. They listen to others, change their minds when evidence demands, and acknowledge uncertainty, but they're still human, and that's okay. Another lesson: unanswered questions drive science forward. If Einstein had accepted Bohr's Copenhagen interpretation, the debate would have ended in 1927. But because Einstein kept challenging, kept asking, "But what is really happening?" new insights emerged. The EPR paper, meant to show quantum mechanics' incompleteness, led to Bell's theorem, which led to experimental test of non-locality, which led to quantum information theory. Pilot wave theory, revived by David Bohm in the 1950s, was inspired by Einstein's conviction that a deterministic alternative must exist. Many worlds' interpretation, proposed by Everett, was motivated by dissatisfaction with Copenhagen's treatment of measurement. All of these developments trace back to the Einstein-Bohr debate. The questions they couldn't answer became the questions that inspired future generations. This is how science works. Progress comes not from settling questions, but from refining them, from turning philosophical disputes into testable hypotheses, from refusing to accept "shut up and calculate" as final wisdom. Perhaps the deepest lesson is this: mystery is not failure. We live in a culture that values certainty, that treats ambiguity as weakness. We want answers, clear, definitive, unambiguous. But the universe doesn't always cooperate. Some questions may not have answers, at least not in the form we expect. Is the universe deterministic or probabilistic? Does reality exist independently of observation? What is measurement? Quantum mechanics doesn't answer these questions unambiguously. Different interpretations give different answers, all consistent with experiment. This drives some people crazy. They want one right answer, but perhaps the universe is showing us something important. That reality is richer than our categories, that existence can't be captured in simple either-or frameworks. Einstein wanted the universe to be comprehensible, to fit into human logic. Bohr said we must accept it on its own terms, however strange. Both were wise. We should strive to understand, while accepting that some mysteries may remain. The Einstein-Bohr debate is not over. It continues in conferences, papers, laboratories, and classrooms around the world. Physicists still argue about many worlds versus collapse, about the role of consciousness, about whether space-time is fundamental or emergent. Philosophers still debate realism versus anti-realism, determinism versus indeterminism, the nature of scientific explanation. And anyone who thinks deeply about quantum mechanics eventually confronts the questions Einstein and Bohr debated. What is real? What can we know? How should we describe a universe that defies intuition? These questions belong to all of us. You don't need a PhD in physics to wonder about reality, to be awed by the strangeness of existence, to grapple with the limits of knowledge. The Einstein-Bohr debate invites us into a conversation that transcends science, a conversation about what it means to be human, to seek understanding, to live with mystery. As you drift into sleep tonight, carry this with you. Two of the greatest minds in history spent decades arguing about the nature of reality. They disagreed profoundly, yet respected each other deeply. They searched for truth, knowing they might never find it, driven by curiosity and wonder. Their debate shaped modern physics. It gave us quantum information theory, quantum computing, and a richer understanding of the cosmos. But more than that, it showed us how to pursue knowledge with humility, how to disagree with grace, how to live with questions that have no easy answers. The universe is strange, stranger than Einstein wanted, stranger than Bohr fully grasped. It's non-local, entangled, probabilistic, and mysterious. And it's beautiful. Perhaps the greatest legacy of the Einstein-Bohr debate is this: the reminder that mystery is not something to fear or eliminate, but something to embrace, a source of wonder, a spur to inquiry, a gift. God may or may not play dice. But whether the universe is deterministic or random, comprehensible or mysterious, one thing is certain: it's endlessly fascinating. And that's reason enough to keep asking questions, keep exploring, keep marveling at the strange and beautiful cosmos we inhabit. And so, we arrive at the end of our journey through the greatest debate in physics, from that pivotal room in Brussels, through thought experiments of breathtaking ingenuity, to modern laboratories testing the fabric of reality itself. If this exploration stirred something within you, a sense of wonder at how two brilliant minds could disagree so profoundly yet remain friends, a deeper appreciation for the mystery at the heart of existence, or simply curiosity about what it all means, I invite you to subscribe to Sleep Entangled for more contemplative journeys where science, philosophy, and wonder converge. Like this video to help others discover the Einstein-Bohr debate, and share your thoughts in the comments. Whose vision resonates more with you? Einstein's quest for objective reality, or Bohr's acceptance of quantum strangeness? This is Sleep Entangled, where the greatest controversies in physics become late-night contemplations. Until we meet again beneath the quantum stars, rest peacefully knowing that the universe is stranger, richer, and more wonderful than either Einstein or Bohr imagined. The debate continues, the mystery endures, and that's exactly as it should be.